Hi everyone, today we're going to look at the end behavior of functions. So we'll start with question 1. The bear population at a wildlife preserve follows the formula P of t equals 2000 t over t plus 1, where t is greater than or equal to 0 is the number of months from December 2010. In the long run, what happens to the bear population? Use your calculator to find the bear population many months in the future, and then generalize about the future of the population. Graph the function on your calculator. Okay, so guys, there's some things that are important to understand before you enter anything into your calculator. The t is the independent variable, and it represents time. P of t is the dependent variable, the y, and that represents the bear population. So when we're asked in the long run what happens to the bear population, we're really asked when t is a very large number, so a lot of months in the future, what can we say about the y values? So what we would do is we'd enter this into our calculator in Y1, and then we could go to second window, and we're going to go down to independent ask. That will allow us to enter our own values for x and get the corresponding y values. Then we'll hit second graph, and we'll get a blank table. And so now I'm going to put in big numbers for the independent variable. I'm going to look at what happens to the y's. So by putting in very large numbers, you will be able to see that in the long run, the y values are getting closer and closer to 2000. They'll never actually hit 2000 exactly, and that's a topic for another day. The reason that you'll see 2000 is just due to rounding in the calculator. But so to write what we see here, in the long run, the bear population approaches 2000. So many years in the future, the bear population will be getting closer and closer to 2000. So in the long run, the population approaches 2000. We also want to write it with limits, which we've been doing the previous days. So the limit as t goes to infinity of this function is 2000. As the t's get bigger and bigger, the y's get closer and closer to 2000. Now the final thing we want to do is look at this graph. So let's get a good window on our calculator so we can see clearly what's going on. Now we're going to go to window. We know that we're only talking about when t is bigger than or equal to 0. So let's put in 0, and we're interested in what's happening when we have big x values. So let's put in a big x value, maybe 2000. As our max. And then for the y's, we know that the y values are getting close to 2000 in the long run. So let's make maybe like 2050 our y max. So now if we look at this graph, we can see that in the long run, the y's are getting closer and closer to 2000. We can see it graphically. So what you learned in Algebra 2 was that a horizontal asymptote is a line, a y equals line, that your function graph stays close to in the long run. So in this case, we have a horizontal asymptote at y equals 2000. Okay, guys, what I suggest is that you pause your YouTube or whatever you're viewing this on now, and then try to do questions 2 and 3. When you unpause, I will have the solutions for 2 and 3 up so that you can check. Okay, so please take a minute and pause this now. Okay, guys, so please check your answers for 2 and 3. And just something that I want to point out in question 3 is that as the t values get bigger, as time goes on, the y values just get bigger and bigger with no stopping point. So there's no horizontal asymptote. There's no one y value that our y's stay close to in the long run. Okay, so now what we're going to do is flip over to the next page, and we're going to try to generalize about what we just found out so that we could come up with the horizontal asymptote and the end behavior for a function without using our calculator. So when we had the highest power in the denominator as greater than the highest power in the numerator, So anyway, that happened in question 2. So let's look at that again. So we had 20t over t squared plus 4. So now we're interested in what's happening in the long run when the t values are really, really big. So what's going to matter the most in the denominator is t squared. Because if you put in numbers like 1,000,000 for t, 1,000,000 squared is so much bigger than the 4. The 4 doesn't matter. So what we find is that this function just reduces, or this end behavior model just reduces to 20 over t. So as t gets bigger and bigger, when we do 20 divided by 1,000,000, this value is going to get closer and closer to 0. So when the highest power in the denominator is bigger than the highest power in the numerator, we have a horizontal asymptote at y equals 0. Now let's look at the example when the highest power in the numerator was greater. So that was in question 3. So we had 2t squared plus 7t plus 5 over t plus 3. So again, let's look at our end behavior model, which is going to be 2t squared over t, which really just acts like 2t. So as t gets bigger and bigger, so does 2t. So in this case, we saw that we would have no horizontal asymptote. So when the numerator has a larger exponent than the denominator, then we're always going to have no horizontal asymptote. So now in question 1, the two exponents, the two leading exponents, were equal. So we had 2,000t over t plus 1. So if we look at our end behavior model, the top really acts like 2,000t, and the denominator really acts like t plus, really just acts like t. So this really just acts like 2,000. So when the exponents are equal, we're going to have a horizontal asymptote at the quotient of the leading coefficients. So we're going to take the number in front of the largest term in the numerator and the number in front of the largest term in the denominator. That tells us where we have our horizontal asymptote. Okay, guys, so please take a minute, pause this, try to do questions 4 through 7 at the bottom, and then unpause it and you can check your answers with what I have at the board. Okay, guys, so the answers for 4 through 7 are up at the board. And just one thing I want to point out is that in the first 3 examples that we did, we were considering real-world situations where the independent variable represented time. And so we didn't consider negative time. But when we have just these like general functions that aren't about real-world problems, we can consider x approaching positive infinity and x approaching negative infinity. And generally, the only difference in the limits would be the signs. It's not 100% true, but in the examples for this course, that's true. Okay, all right, thank you.